Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Welcome again, everybody. I hope you had a very nice evening last night after the incredibly exciting sessions we had yesterday. So today we are going to have the UPCRC workshop. This is what Microsoft calls the third day event after the Faculty Summit. And oftentimes what happens during the Faculty Summit is people just have these short times to present general directions of research. So this session is so that we can take deeper dives into the topics. We worked with Illinois, Intel, and Microsoft to get this program ready. And we are going to go, instead of in the Faculty Summit, just on presentations by the partners, we decided to go by teams. So the teams are programming systems, tools for parallel testing and debugging, applications, architecture, and at the end, like yesterday, we'll have another panel that we hope is going to be as excited as the one we had yesterday. And the panel is going to be UPCRC, Can Industry and Academia Collaborations Be Effective? We hope that there will be a lot of discussion, debate, and we hope we can have great conclusions. So a few remarks. If you want to connect to externally through wireless, there is a username and a password out there. And we have buses coming back to the Hyatt Hotel starting at 5, and probably the last bus is going to be about 5:30. So once we finish the panel, we just have to go out and rush for the bus. If you could please sign, if you have not done that, sign at the door so that we know who is coming and the affiliations and your names. And with that, I'd like to introduce our first speaker, David Padua. He comes from the University of Illinois, where he has been since 1985. And when I do these presentations, it's always difficult to omit some of the remarks because everybody who is talking today has such a distinguished career that I struggle to find what to say during less than 1 minute so that we can spend most of the time listening to them. So David has been a professor in Illinois since 1985. He has a very distinguished career, and probably the last book you wrote is the Encyclopedia on Parallel Computing. And I don't want to say more because we know pretty much very well his great accomplishments, and David is going to talk about abstractions for parallel programming.
Thanks. Of course, the last book I wrote, I didn't write because it was an encyclopedia, and that's
Those are the nice ones.
right. And that was a very pleasant experience, the encyclopedia. Many people contributed. It was very moving to see how much people were willing to participate in that project. Okay, so I was asked by my colleagues to give you a summary of the work going on at Illinois. That's a very difficult task. So the work going on in Illinois in the area of compilers and languages. So I'll try to do my best. But first, I must say that what I'm going to say is not comprehensive, neither in terms of the projects, nor in terms of the people. So there are more people doing compilers, there are more compiler projects going on, but I'll mention a few that seem more relevant to this meeting. So mainly, I'll focus on the work of Vikram Adves, Wayne Mehus, and my research group. And will be presentations on compilers and the languages that are being designed. So let me start by saying some common places about what the problem is. So as we know, parallelism is everywhere. And if parallelism is going to succeed, it will be that because software will be developed that can take advantage of parallelism, okay? But when that happens, and if that happens, one of the things that obviously is going to happen is that there will be a dip in productivity, because writing parallel programs is more complex than writing sequential programs. You need to deal with performance, scalability. There are new sources of defects, and so on and so forth. Okay, so what we face as a challenge as software people is facilitate parallel programming, reduce the impact of parallelism on productivity. It's not very glamorous, but it's true. That's all we are trying to do, reduce the impact, try to bring back productivity to the level of the sequential era. And we find a lot of challenges. Well, of course, optimization, because performance is crucial in the parallel realm, because only through scalability, new machines, through the scalability of software, new machines will be valuable and people will be willing to buy them. So it's a business model. There is the issue of portability. That is also tremendously difficult because while porting across machines in the sequential era was relatively straightforward, because the difference was in the type of instructions and perhaps a few of the classes of instructions. In the case of parallelism, the classes of machine can differ widely. There's a big difference between a GPU and a collection of CPUs, and there is a big difference between vector processing and distributed memory machines and so on. So there is a tremendous issue there. So that's a problem that has never been resolved, and we really don't have a good answer how to guarantee that you write a code that will be executable on a variety of classes of machines, distributed memory, shared memory array, and so on. And the other challenge, of course, is correctness. There are new classes of defects, non-determinacy, deadlocks, and other issues related to parallelism. So how do I address this challenge? From what I have seen, there are mainly two strategies that I believe are viable to address the problem. One is to raise the level of programming so that you have enough information to be able to map across machines that will facilitate portability. You have enough information to do optimization that will solve the problem of getting good performance and scalability, and so on and so forth. And that, of course, is a difficult problem because at what level you present the language is not an easy issue. You may want to work at the level of the application and have abstractions that represent complete applications, or you can have abstractions that represent algorithms, or you can have abstractions that represent kernels. Which ones are useful, how you combine them is not a problem that is easy to solve. So and there are a number of possibilities. You can work from the formula level, or the very general description level. You can have domain-specific languages, you can have very high-level operators, and you can have just plain parallel abstractions like parallel loops and co-begin, co-end, that sort of thing. So that's one. And the other, which I think is also crucial, although many people don't seem to be fan of this approach, is to have techniques that automate the process of optimization, automate the process of porting, and so on and so forth. So we actually need to work on this area of auto-tuners, compilers, and so on and so forth. So and I did this a couple of days ago, but I'm thinking about that. Maybe I'm missing something, but I think certainly these are two of the main strategies that we can use to address the problem of productivity in the parallel world. So let me start by going quickly over what is being done at Illinois, and I hope it's not too boring. It will be just a short description of projects. So 3 projects in the language realm. Triole, that's Wayne Mayhew's group. This HTA work that we have been doing in my group, and the Hydra thing. I'll describe these things very quickly to you. So Triole is is a library of built-in functions that you can use from basically, here is an example, is basically a library that you can call from Python codes. And I think this work is similar, I guess, to the work that is going to be described in the talk after this one. Basically has a number of operators with iterators, and the idea is that the operators are implemented in parallel, and you can work in the programming at the high level using the conventional notation. Okay? That's, the notation is Python. And I think that's all I am able to say about this. They are working on compilation techniques and so on, and they continue working in this area. And this is the work, as I was saying, of Wen-Mei Hu and his student Christopher Rodriguez. Right. That's one project, and here, as you can see, the goal is to raise the level of abstraction, have functions that implement operations, and you encapsulate the parallelism within the functions. The other related approach is the one in my group on hierarchically tiled arrays, and this is work that my students, colleagues, and I have worked for a few years. And basically, the main idea, as Josep described yesterday, is that we recognize the importance of blocking and tiling as a first-class object. If you look at algorithms for parallel computing, sequential algorithms dealing with locality, the tiles appear over and over again as a constant. So having them in the language explicitly, we thought was a good idea. In reality, this started when we had the HPCS program started by DARPA, and the IBM guys wanted an extension to MATLAB for parallel programming. And by looking at MATLAB, I decided that some of the structures they have this, I now I forgot the name, they have some classes of objects that basically are collections of arrays and enable the hierarchy of tiles. I thought that could be used to represent parallelism. The idea is relatively simple. You have arrays that are tiles, and the tiles can be tiled and so on. And then you can use the tiles at the top for distribution across machines, the tiles within the tiles for locality at different levels. You can use the tiles at the second level for shared memory parallelism and so on and so forth. So it's a natural thing in the hierarchical machines of today. And then we have worked more recently in extending these notions to irregular data structures like sets and so on. So here the operations are on arrays and sets, and the idea is that the arrays are tiled, and you can represent by manipulating these objects parallel computations. Okay? So that's basically the idea. I am personally still struggling with the notion of what primitive you need to go beyond linear algebra, and also struggling with the problems, do we need to go beyond linear algebra? You can do everything with linear algebra, perhaps. So that's an issue that I don't think I can answer. But what I can say is that our work on irregular structures proved to be very, very effective. There is a tremendous complication in tiling not regular structure, because you need mechanisms to decide where each component of the set will go. And we can make those mechanisms, but it's not obvious how to build them from scratch. You need to think very hard. So the end result with this notation, of course, is that you can get codes that are much more compact and more importantly, more readable than the equivalent MPI codes. And the other advantage of this approach of having all your computation with a parallelism encapsulated inside operations on these arrays is that you have portable programs. You can implement the operations as GPU kernels. You can implement them as threads within MPI. You can implement them as parallel loops. And they, in all cases we have tested, they work reasonably well. All right, so that's that. And then the other project that I just wanted to mention briefly is another one in our group. It's called Hydra. And that is with my students, Alexandre, Duchateau, and a colleague from the University of Bordeaux, Denis, Barthou. And the idea here is to start with a formula. And for example, you want to find x in that equation. And then what we do is we tile the different operators and convert the equation into multiple equations and looking for a recursion. So eventually, this reduces, if you want to go all the way to a scalar equation that is easy to solve, okay? So in the process of decomposing the equation, what you find is a number of operations that can be executed in parallel, and by doing the composition, what you build is a graph of operations that can be executed in parallel. Okay. The great advantage of this approach is that you can partition the components in multiple ways, and that enables you to search the space of possible solutions and look for a good performing version of the algorithm. We have still the preliminary stages, but what we have seen is that the codes that result are very good and competitive with what people have written by hand. So stay tuned, there will be more about this in the future. Okay, next project is about compiler evaluation. This is a topic that I think is tremendously important because while you see a lot of publications about new compiler techniques and strategies and so on, what you don't see too much is evaluation of what exists out there. And compiler technology is not just about algorithms, it's not just about ideas, it's about how well our algorithms work when applied to real programs. So it's a tremendously difficult problem to do evaluation of compilers, not so much for the conceptual issues, but the labor involved, because you need really to do manual analysis of what is happening to really understand how well the compiler is working. So here is a project that we did for 2 years at Illinois, the evaluation of auto-vectorization. So what happened is the Blue Waters project, in the Blue Waters project, the idea is to program the machine with MPI codes. But the thread within the MPI program has to execute as efficiently as possible, and what they wanted is automate the process of tuning for vectorization, to take advantage of the vector extensions of the microprocessor, the Power 7 machine at the time. So they asked me to work with the IBM compiler people to make sure that they deliver a compiler for the Blue Waters that will produce good performance, especially in the context of taking advantage of the vector extensions. So this is regarding Tim Matson's comment yesterday. So in reality, this is a form of autoparallelization, and of course, the issue is not whether it's impossible or not, it's a matter of degree, because typically what people do is run their program through the compiler, and whenever it can find vector extensions, they just, vector operations, they profit from that and benefit from that. And in reality, it's a very important technology, so much so that all compilers auto-vectorize. And compiler groups invest a lot of time in this technology for many reasons. One of them, of course, is that you evaluate machines by how well they perform on spec codes. And if the compilers do better at vectorizing, the machine looks better. So there is but there is also, I think, a real relationship of auto-vectorization to regular users all over the world. Auto-parallelization, I think, is also true that all compilers auto-parallelize. But when you talk to the IBM compiler people, they hear very little about users of auto-parallelization, but auto-vectorization is widely used. And, of course, why not? You can have computers that answer all sorts of questions. No reason why a computer cannot answer auto-vectorization questions. Can this loop be vectorized? So let me just tell you briefly the outcome of the evaluation and briefly what we are doing going forward. So basically, we look at we took the collection of loops that David Callahan and Don Garra and Levine put together 20 years ago, and ran them through 3 compilers, GCC, ICC, and the IBM compiler. And what we found out is that there was a great variability in what the compilers were able to do. And despite the fact that at some point we gave the benchmarks and the results to the different compiler groups, still after a while, and the compilers kept evolving because of that, after a while you can still see that there were loops that were vectorized by some compilers and not by the others, and with no good reason for that. So basically, I think the most important lesson I learned is that we have tremendous difficulty figuring out how to do quality control in compiler development. So that to me is the biggest reason, because when we look at the loops, there is no reason why they cannot be vectorized. We have the technology, we have the mechanisms to do the transformation, to do the analysis. The only problem is that the compiler just doesn't know how to take all these tools and put them together and do the appropriate thing for a particular job. It doesn't know how to seek the.
What do the numbers in the shaded boxes mean, the 2 and the 3? No, on the auto-vectorized. Under ICC, you have a box with a 3, and then under GCC, a box with a 2.
To tell you the truth, I don't remember right now. There is a paper in PACT last year, and they describe all the details there.
So the compiler rocks.
Huh?
I mean, if I look at this,
the intercompiler. Well, okay, this is not the end of the story. This is only the loops that were very simple. When we took the real applications, all the compilers behave equally badly.
yeah.
30% of the loops were vectorized. Performance, when you did the work by hand, as if you were a compiler, you can get factors of 2 or more of performance improvement overall. So there is a lot to do, but in all cases, real applications are not. When you look at the transformations that you need to apply, they are there. We know the transformation. There is nothing new that needs to be learned about analysis of or transformation. What we need to learn is how to guide the compiler, how to establish a path to take the code from the original form to a form that performs well. If you just launch a compiler and say search if there were no tomorrow, then we'll get good performance for sure. The problem is compilers must be efficient also. They cannot take a long time to compile, and that's part of the reason. And you know, the problem of optimization is a black art. Nobody knows exactly how to search that space, but I think that's the major problem. Yes?
So in the loops, what programming language are they in?
C.
And your analysis was that from language perspective, they are legal to vectorize?
Yeah, of course. And in fact, all these defects or lack of effectiveness of the compiler was after restrict and align keywords were inserted by hand. So even then, it didn't work.
I'd like to insert an editorial comment. If you are interested in vectorization, reading that original paper by David and Jack and so on would be worthwhile. I mean, just to see what can be vectorized and you know how one might test the ability of a compiler to discover.
Yeah.
It's an interesting paper.
It's very interesting, and when you look at that, you also read this one, and one thing Said did is compare the effectiveness of vectorizing compilers then and now.
Yeah.
And they are not better now, as you will see. Okay. So then the next, I have 40 minutes, right? So I have.
No, it's 30 minutes.
Okay, so let me just. 30 minutes. Okay, so let me very briefly describe in 2 minutes what other things going on. So there is, of course, compiling OpenCL, and I'll tell you one is a translator developed by Wayne Hu's group that transform OpenCL depending on the target machine for vectors, multi-threading, sequential, and so on, and it's very effective, as you can see here, and they are still working on that. Then there is work also by Wayne Hu on data layout system that reorganizes structures of arrays of structures into tile information, and also very effective mechanism to reorganize the data. This is an area of great importance to be able to restructure the data to get good performance. And then finally, we did some work on tiling and overlap tiling and hierarchically overlap tiling that was very important for certain classes of applications. We are now working on n-dimensional tiling and overlaps of using this tiling to overlap communication with computation with some success. And then finally, the other project, and Shoaib described this yesterday, is the work on deterministic parallel Java. And basically, as you know, the idea is to insert declarations in the program and have the compiler infer what regions of the data are being modified by the different threads in the program, and determine whether or not the program will be deterministic or not. Let me just say there are novel features of DPJ not available before. For example, the availability of nested regions, which is very important when you're traversing trees, for example, and the support for array-based computation, which of course is crucial. And I'm going to skip this. The other thing important they did is they allow for non-determinacy. So you can have non-deterministic programs, non-determinate programs, and check still for the absence of races. So they are sure that the data that conflict is enclosed within an atomic, within a critical region. Okay, so that's that. So programming systems for parallel are still evolving. There is a lot to do. The truth is that the problem has proved more complex than we expected along all dimensions, but much progress has been made, and we'll keep working on it. We of course will never solve it completely, but the current situation is pathetic, so we need to do much more. Thanks.
Selective embedding, just-in-time specializations. And this is the main bed that UC Berkeley has been working on, as you know. And Shoaib is graduating from Berkeley and is taking a postdoc at MIT. Is that right, Shoaib?
Yes, that's right.
And if you please repeat the questions, because we are taping the presentations. So, thank you.
So I was told to make sure it's the right resolution. Okay. So I'm Shoaib Kamil. I'm from UC Berkeley, where I've been a grad student for a few years. And I'm going to be giving some updates on SEJITS, which is Selective Embedded Just-in-Time Specialization. This is our technology for enabling high performance from high-level languages. And it was really good to see some of the stuff that Professor Padua just talked about, because one, it looks like there are other people doing similar things, and two, the motivation was all there. So vectorizing is arguably the easiest form of autoparallelism, but And the technology to auto-vectorize is known, but it looks like it requires somebody to guide the use of that technology. And that's kind of the approach we've taken. So just to remind you what selective embedded just-in-time specialization, or SEJITS, looks like, we want people to be able to write in these productivity languages like Python. So their application has portions that just run on the interpreter and use the normal Python infrastructure. But there are other portions of the program which pass through domain-specific embedded language compilers. And these compilers use the infrastructure we've built, which is called ASP, to intercept these calls and translate the function in question into a low-level language. That translated function is then compiled and dynamically loaded into the interpreter, which then calls that function and returns the result to the user. So all of this looks like, from the user perspective, that they're writing in Python, but what's really happening is that portions of that Python code are being translated into C or C++ or CUDA or other low-level parallel language, compiled and run, and the result returned. We also introduce caching so that this just-in-time compilation doesn't have to happen all the time, only the first time something is run. So here is an example of an actual kernel that we can specialize using the stencil domain-specific embedded language. If you look, it looks just like Python code, if you're familiar with Python. Lots of colons and indentation. But what this computation is basically saying is, for each of the interior points in a multidimensional grid, for each of the neighbors of that point, apply this particular function. So we treat this kind of like a declarative specification of the computation. So even though it looks like usual imperative programming with a for and so on, all this is actually doing is telling the infrastructure what the computation is, not how to do the computation. In particular, there are certain constructs here that are domain specific. So the first thing is that we inherit from a particular class. This is what tells the infrastructure that this computation is something that needs to be specialized. So the initializer for this stencil kernel class is the thing that looks at the source code and does all the steps that I'm going to describe in a minute. We also have these special iterators which are used in the program translation. So the first step is to introspect this function and get the abstract syntax tree. This is done mechanically, automatically, using Python infrastructure. We didn't have to really implement anything for this, right? Python can introspect itself. So you get this syntax tree that represents the computation. If you look closely, you'll see there's a function definition, and there's these for loops, and lots of other nodes. So we use that AST and do a mechanical translation to a domain-specific intermediate representation. So there's some effort required for the person writing the domain-specific embedded language compiler to write this translation from that Python AST into this intermediate representation. Now the intermediate representation looks like a tree. It has some domain-specific constructs, but again, what it really is representing is not how to do a computation, but actually the declarative specification of what that computation is. This is done in our infrastructure by writing simple tree transformation rules that work on local pieces of the tree. It uses our infrastructure and the visitor pattern to make it as easy as possible to define. The point of this translation is, once you get to this point, we can run correctness checks, we can ensure that, because it's a declarative, we can do things like make sure that the specification is correct by construction, as in when we're translating it, we make sure that everything we're translating is going to result in a correct specification. So most, if not all, of the checking is done in this portion of the compilers. So from there, depending on the target machine or what the actual code is running on, it is translated into a back-end domain, a back-end general AST. So an AST in C++ or in CUDA with parallel constructs, et cetera, et cetera. And then that tree is then optimized. Now this is where most of the domain-specific knowledge is used, or the expert programming knowledge is used. So in this process, you figure out, well, for this particular construct, I translate it into this kind of C++, and I know that I can do certain optimizations on this. As Professor Padua pointed out, there's often cases where the user who is writing the code knows that a particular transformation is correct. However, the compiler does not have the absolute knowledge in order to know that. Common example is things like loop unrolling. Now, certain cases, the compiler can prove that this is a correct transformation, but that's not in every case in which it would be correct. In this particular example, I'm an expert in stencil computations. I come from the high-performance computing world, so I know how to do this. I know how to make a stencil computation go fast. So all of my knowledge is embedded into optimizing this tree. We've also implemented many of the common compiler optimizations, things like loop blocking, loop unrolling. These are things that are part of our infrastructure, so you just need to apply them in the proper way. So what does the code kind of look like? Well, you end up with so this is actually a very simple example of what comes out of the code I just showed you. And this is a simple example in that, it's 2D, it only has a couple optimizations applied. So just so you don't have to squint, there's parallelization here. There is cache blocking, which ensures that you work on a working set-sized cache block at a time. And there is loop unrolling or register blocking, which helps expose things like vectorizability. It also helps expose things like common sub-expression elimination and so on. So this is the code that gets passed to the compiler. And as a bunch of the auto-tuning work has shown, if you write your code in a particular way, you can get the compiler to give you much better performance than writing your code in the most naive way. So that's what we're doing here. I've left out a couple of the major pieces of what SEJITS does. For example, I just mentioned auto-tuning. I haven't shown you any of that, but basically we generate many different versions, and on each invocation of a function, we run a different version until we've explored the space completely, and then we use the best version for subsequent invocations. So this is SEJITS. For the rest of my time, I'm going to give some updates on the current domain-specific embedded languages and libraries we have, show you some new results, some users and upcoming releases, and finally talk a bit about some future directions and what we're doing. So first off, this is kind of the set of implemented domain-specific embedded languages and libraries that we have. The red ones I'll give you some more detail about, but let me talk briefly about a few of these. The platforms we target range from x86 plus OpenMP to MPI to CUDA to Silk Plus. So we have basically every backend. We even have a cloud backend at this point. I want to let me just briefly describe each one. So the first one is for stencil or structured grid computations. I'll spend some time talking about some results from that. The second one is for graph algorithms, and I'll spend some time talking about that as well. We've also implemented a simple parallel map domain-specific language, which basically lets you compose these languages with map. So you can do high-level parallelism there. One of the big success stories, I would say, is the Gaussian mixture modeling library we have, which has been released. I'll talk a bit about the infrastructure that's a part of, but that's able to get performance that's 250x real time, faster than what the domain scientists were using before, which was handwritten, hand-optimized CUDA. We also have a matrix powers communication avoiding library, which I'll talk a bit about. And we have 3 new domain-specific embedded languages that are under development right now. So the first one is for the bag of little bootstraps algorithm, which is a statistical analysis tool. And this one is used by people who want to evaluate machine learning and other kinds of things. We have a version that can target Silk Plus on a local multi-core machine, as well as a version that can run on top of the Spark infrastructure in the cloud. So that's under development. We also are working with the people who make GraphLab, which is a C++ parallel library for machine learning using the graph representation. We're working with them to replace their current API. Their current API does something quite convoluted. So first they created a Java API for their C++. Then they used JPython or Jython to write a Python API on top of the Java API on top of the C++ API. So we're getting rid of all of those layers, and we're using our infrastructure to replace the current API so that you can get C++ level performance while writing in Python for your graph algorithms. And finally, we are working on a communication avoiding parallel recursive structural pattern. So what this comes from is the insight that there's lots of algorithms that have a particular recursive structure. And this particular recursive structure allows you to choose at any point whether you want to run the different leaf nodes of the computation in parallel or whether you want to run them serially, depending on the available resources. So a preliminary implementation of this was applied to matrix multiply, just the standard thing that has been optimized the hell out of. But we were actually able to beat MKL, Intel's math kernel libraries, using this particular recursive structure. Now we're using MKL by using MKL, but being more intelligent about when to do things in parallel and when not to do things in parallel. So first, let me talk a bit about performance that we're getting out of the stencil domain-specific embedded language. This is a set of benchmark kernels on the x-axis. On the y-axis is the fraction of peak performance. The last set of bars is the geometric mean, and we're comparing against Pochoir, which is the state-of-the-art domain-specific language for stencils using Silk Plus. It's developed by MIT, and it gets excellent performance using the cache-oblivious algorithm. So we are able to get a geometric mean of 93% of peak performance. And this peak performance comes from looking at the kernels and finding out that they are bound by the memory bandwidth performance of the machine. And 93% of peak performance is quite a bit better than you could get in Python. Just as a order of magnitude kind of thing, each of these is about 2,000 to 3,000 times faster than what you would get by writing it in Python.
So where did you run this?
So this is a single node 4-core i7 machine. We compared to the autoparalyzer in GCC, which uses the polyhedral framework, and we're able to outperform that by up to 11x, and about 2.5x faster than Pochoir. And as I said, the geometric mean here is 93% of attainable peak. Yes?
This is the first time I get to see comparison of DSL and Pochoir on the same hardware line.
That's right.
Fine.
Yes. Sorry? Oh, the question was, this is the first comparison that Robert has seen on the same hardware for Pochoir and our infrastructure. So I mentioned the communication avoiding. Sorry.
The language, right? The difference is that they generate cache oblivious algorithm and you generate cache aware algorithm.
Well, so the question was, the difference is not due to language, whether the difference is due to language or whether it is because they're using a cache oblivious algorithm and we're using a cache aware algorithm. Well, I think the difference is, well, it's certainly not due to language. We're both using C++. We're both using the Intel compiler. But the difference is due perhaps somewhat to the use of cache oblivious algorithm versus cache aware algorithm, but I think it's more so that because we're doing our compilation just in time, we have to us available every parameter that you would possibly inline into the computation. So we know the sizes, which tells us what kind of blockings are valid, and we explicitly generate all the valid blockings, and we use auto-tuning. So I would say it's probably more related to our use of auto-tuning than it is to the algorithm, because conceptually, if you look at the algorithms, they do the same thing. However, because we can use auto-tuning, we're able to get the fastest possible performance from a wide variety of code variants.
Adding auto-tuning to their process as well.
So the question is, they have a way to add auto-tuning to their process. Is that a statement, or are you asking me? Oh, so I am not aware of this functionality. When I presented this in front of the Pochoir people, they think they can improve their performance, and you know, I'm sharing the code with them, so hopefully we can figure out how to make their performance better. So the other thing I wanted to talk about in terms of performance results is that we've talked a bit about our communication avoiding matrix powers library. And what this particular kernel does is it's a building block of communication avoiding Krylov subspace methods. And what this chart shows is the performance of 3 different implementations of a communication avoiding CG solve. I'm sorry, 3 different implementations of a CG solves, one of which is communication avoiding. So the first one is kind of the standard, the blue is the standard CG that you would get if you're writing in Python and using a good performance library. This is SciPy, which basically implements all of the MATLAB functionality in Python. It's what most people use when they're doing this kind of computation in Python. The red is using Intel's MKL, and the yellow is our communication avoiding CG with matrix powers only doing 1 matrix multiplication at a time. So this is kind of the baseline that you can compare with the non-communication avoiding stuff. And the green is communication avoiding CG using our matrix powers kernel. The dark bottom parts of the bars are the time spent in the matrix powers portion of the CG solve, and the matrix multiplication part of the CG solve, and the light bars are the rest of the computation. What this really is showing is that if you look at just the matrix powers part we're able to outperform Intel's MKL by 2x, which results in much faster solves. So I want to talk a bit about some new work that we've been doing in collaboration with people from UC Santa Barbara. And we've been working with a Python infrastructure that they've built called the Knowledge Discovery Toolbox. And the Knowledge Discovery Toolbox is basically a high-level graph algorithms library for domain scientists. So most people will use the KDT to run their graph algorithms, do things like breadth first search or clustering and things like that. It's built on top of the combinatorial BLAS, which is a low-level C++ with MPI library that casts graph algorithms as linear algebra operations. And that uses MPI and can use OpenMP, Silk, and things like that. This is not yet implemented. That's why it's in a dotted line. So we're adding in the SEJITS infrastructure here to bridge the performance gap between things that are written by domain scientists and things that are written by people at the low-level distributed combinatorial BLAS. An example of this is a domain-specific embedded language for filtering. Now, oftentimes you have a graph that has attributes on the edges or the vertices, but you want to perform your graph algorithm only on a subset of this graph. So for example, you have phone calls and texts, and you only care about performing your graph algorithm on the phone calls. So what we've done is we've implemented a domain-specific embedded language that allows you to write filters. And the filters are basically functions that return true if this edge should be included and false if it should not. KDT itself has infrastructure for doing these filters, but in KDT the filters are written in Python, and at each edge during the graph algorithm, it has to upcall into Python and decide whether this particular edge should be included or not. So that incurs a pretty big performance penalty. So our domain-specific embedded language uses Python. It uses the same kind of infrastructure to write that. Here's an example of a filter that checks, if the count is greater than 0 and if the time is less than some particular time you've passed in. And these are edge attributes of the graph. So using this, we can speed up the performance quite a bit. So here's a graph that shows the mean BFS time on a log scale on the left side, and on the x-axis is filter permeability. That's the percentage of edges that pass the filter. The performance that you should be comparing is the green, which is KDT's current implementation that, like I said, runs in Python, and the blue, which is the one that uses SEJITS. Now, in order to build a baseline for this, we also implemented the same thing at the low-level C++ library just to compare. Now, this isn't something that we would expect a domain scientist to be able to do because it involves writing low-level C++ parallel code, but that gives a good baseline. In any case, the performance here is 5 times faster than the current KDT, and the slowdown versus writing the whole thing in C++ is 25 to 50%. What I'm showing here is performance on 36 cores of a 40-core Xeon 4-socket machine. We've also run this in the distributed setting on Hopper at NERSC, which is a large-scale AMD. It's a large-scale Cray XE6 using AMD processors, and we've seen similar results there. So I'm going to switch in the last few minutes I have here and talk a bit about what's going on with users and so on. So we've had over 1,000 downloads of our ASP infrastructure from the Python package index, which is kind of the mechanism for distributing Python packages. The KDT work I showed you is going to be integrated into mainline KDT and released this year. This is going to be, kind of the first major outside users releasing something using our infrastructure. And the goal is that the second DSEL we've implemented there, which I haven't really talked about, is also going to be part of the release after that. In the first 2 weeks after the Gaussian mixture model library was released at the ACM Multimedia Conference, we had over 800 downloads of that library. And we have outside users at Carnegie Mellon and other places that are using this in production to replace their current C++ code. Yesterday, Tim Mattson showed some numbers on an application which does protein docking. This is an application that was ported by Henry Gabb, who was at Intel at the time. And it gets 290x speed up by running in the cloud without any change to the ported application. And finally, Tim's also developing a FFT specializer and giving us great feedback on things we need to work on in terms of usability and in terms of making it easy for people to develop these domain-specific embedded languages and auto-tuning libraries for Python. So some future work. So right now, the auto-tuning and the results I've showed you is kind of doing the most naive auto-tuning, which looks at all the particular versions and just runs them in some kind of random order. So we think by adding machine learning, and we have some evidence of this, we can get much faster searches that converge on the optimal version. So there was a paper by Archana Ganapathy and Kaushik Datta a couple years back for stencils that shows that machine learning can greatly improve the speed of converging on the best version. So we want to integrate that kind of search into our infrastructure and make it easy for other people to use in their specializers, in their domain-specific embedded languages. Some of the ideas from SEJITS are also finding their way into hardware prototyping. I think Krista is going to talk about that later on today. And we're also exploring one of the big problems in using these, which is composition. And one of the directions we've seen is that pattern-based frameworks that are used for a particular kind of computation or a particular class of programs, such as multimedia programs or other things like that, is a good test bed for bringing composition to these domain-specific embedded languages. So there's some work from Berkeley that's also going to be talked about later today called PyCasp, which is building a infrastructure for doing multimedia applications in Python and get fast performance from that. So it consists of a bunch of library components, some customizable components, and structural patterns that you can put together in different ways to build your application. There's going to be a whole talk on that later today, so you'll hear much more about that. So to conclude, we've seen really high performance in kernels. We've seen examples of applications authored by people at Berkeley and also people outside of Berkeley that are using this infrastructure to build real applications. We're doing some work on composition, and we think that this infrastructure and ideas from it are really critical for enabling agile hardware, software, co-design, and design space explorations. Thank you. And lots of acknowledgements because there's lots of people who worked on this.
Questions for Shoaib? If there is a question.
Yes.
On your previous answer that what gives you the performance is that you are legitimately taking advantage of that. Do you have sensitivity studies on how much you gain by that?
Yes, and I can show you a graph offline. Yes.
What was the question?
So the question was, do you have sensitivity studies on how much performance you gain by using auto-tuning. And I certainly do. It's in my thesis, so I can show you a graph.
In terms of correctness, what type of effort did you make? Formal verification, other?
That's a good question. So we're working with Kaushik Sen on some correctness infrastructure that allows you to basically prove that the generated code and the original code are doing the same thing, or at least the intermediate results are correct. So in terms of the stencil stuff, the correctness is more so embedded in the domain knowledge. So we're not doing formal verification online for any of this stuff, but we have applied those techniques that Kaushik Sen and his students have come up with, and actually proved that that the stencil DSEL is outputting correct code.
Some kind of equivalence verification taken from the
Yes.
hardware domain to the software domain.
That's right.
Just an additional comment on that. Some of the transformations that are doing specific, use associativity and distributivity of arithmetic to do the transformations, and that changes the floating point properties. So you don't get exactly the same answers. And sometimes they can be very different, and a lot of domain knowledge is required to know which transformations are okay.
So Jim pointed out that the domain-specific transformations we're doing do assume associativity and commutativity and other properties of floating points. So they can change the answer in terms of the floating point correctness. So that requires having domain knowledge of what things are okay to do and what things are not okay to do.
The last speaker for the session is David Callahan. David is a distinguished engineer at Microsoft. He has a PhD from Rice University, and he spent some time at Data Computer, Cray Computer, and since joining Microsoft, he has been working on parallelism and concurrency, and he's going to talk about his latest toy, C++ AMP.
Good morning, everyone. Thank you for coming to Redmond. I'm delighted to have a chance to talk to you a little bit about what we've been doing in Visual Studio in parallel programming. So Developer Division has two broad products. One is Visual Studio, the other is the .NET developer platform. And our broad mission is to make sure that developers are successful targeting Windows platforms, of which there are a great variety for them. I've sort of been at Microsoft for 6 or 7 years now, helping to shepherd along the parallel programming assets. We made a big investment in Visual Studio 2010 around Multicore. And tomorrow, I think, we'll have a member of my team come and talk both about that and the extension work that we're continuing on. Next one. Today, I'm going to talk about C++ Accelerated Massive Parallelism, or C++ AMP, which is really our offering to sort of tackle the problem of GPU programming. So let me give you a little context here. Now, we know Moore's law continues, but the hardware architects have been talking about power for years now. And so sort of a natural conclusion of that combination of cheap transistors but can't turn them all on is that we'll see specialization of silicon to particular workloads, and this is sort of already somewhat pervasive in a lot of places. And one of the really important workloads that exists is the rendering workload manifested that's today sort of handled by GPUs. So this combination of factors have led to a really fast evolution about what GPUs are and where they're used. So part of it is in the programmability of the GPUs, and I'll start sort of 6 years ago when NVIDIA introduced C for CUDA and said, hey, you don't have to work in a graphics framework to get the power of the GPU available to you. And once they made that transition, they were sort of put on this path of making GPUs programmable like CPUs in ways they'd never been before. Subject, of course, to the fact that graphics is the workload that matters, so they're still dominated by engineering for that workload. 3 years after that came out, we saw that the execution model that was sort of pioneered in CUDA then became standardized both in OpenCL and in DirectX 11 Compute. So the two major client operating systems both embraced this model and went forward with it as a core capability. Along that same time, of course, we saw the rise of mobile form factors as a huge concern. They embrace this rich visual experience, now coupled with touch, and that interactivity with the visual experience is something that's only delivered through a specialized hardware solution, an integrated GPU in that solution space. NVIDIA also built out special SKUs saying, hey, this stuff will work in a server environment as well. And they'll tackle the HPC market as aggressively as they're attacking the mobile market. At the last GPU technology conference they ran, they had a factoid about the growth of this at SC, where in 2007 there was one booth that talked about GPUs, but last year 80% of the booths were talking about GPUs. A big impact in the HPC space. And of course now you can go rent those GPUs by the hour at Amazon first and then other places. And then the last step of this trend was the embracing of moving these specialized hardware capabilities onto the main CPU die and building a composite heterogeneous package. AMD released their first APU last year, and the Intel Ivy Bridge, which Intel's had graphics accelerators as integrated parts for a long time, but this one is a DX11 compliant part and is really a candidate for producing the compute workload that we're interested in. So in this context then, we started investing about how can we make this sort of emerging sort of commodity platform, a heterogeneous platform, accessible to a very broad range of developers. So that's what we built in C++ accelerated massive parallelism. Focus on data parallel algorithms, which are the part of the sort of algorithm pattern space that are most effectively optimized by these wide new generation of vector processors. Embrace the heterogeneous nature of the computing, so it's not just one kind of processor, but two you must deal with. Put this in a mainstream context, so put it into C++ and give support in a major IDE like Visual Studio, which will support not just the language, but also debugging and profiling, and get tools in the hands of users that can use this effectively. 4, productivity and portability, and performance. So balancing these three is sort of the design challenge in the API. So this will be now part of Visual Studio 2012. It's available in a release candidate now. Our approach to it was to say, hey, this is just part of C++. So you build a C++ app, you include our AMP header, suddenly you can be doing GPU programming. It's just sort of part of the product, not a special bolt-on, add-on. And that goes all the way to how we think about acquiring the tools and how you deploy the resulting opportunities. We do not think, however, of this as a Microsoft technology per se. We have a first implementation, but we think that this is the direction that the C++ community should move. We created an open specification for our API design and put behind that the Microsoft Community Promise, which will guarantee a royalty-free license to whatever IP you need to implement this spec. And we are actively looking to have implementations on Linux, on Android, and Mac OS. At its core, AMP is just an STL library, but there's a couple of extensions to C++ we made to actually enable targeting of the diverse range of hardware that we're interested in. I will dig into those. One of them is a pretty novel extension. The other is a tweak on sort of an existing idea. Our implementation is a layer on top of our graphics platform support DirectX 11. However, DirectX 11 doesn't shine through, so it should be feasible to build an implementation on top of OpenCL or even perhaps OpenGL. We haven't done that, but our intention is not to make DirectX shine through, except in some interop APIs. Give you a very brief introduction to the core concepts of what is in C++ AMP. Starting with matrix multiplication, I'll do a very simple implementation, and later in the talk I'll do a more sophisticated implementation that'll give a more substantial performance advantage. So here's our starting point, a simple C++ version, the usual textbook 3 loops, inner product in the innermost loop. The 2 outer loops are then completely parallel. The interface starts with C++ stood vector types and some explicit bounds passed in. You know, one of the weaknesses of C++ is it hasn't actually standardized on a multidimensional data type, which is pretty important to do data parallel programming with. So one of the things then we added in C++ AMP, and this is an essentially complete C++ AMP program, subject to missing an amp.h header and a namespace inclusion. We added a notion of an array view, which allows you to overlay onto an existing linear data structure a multidimensional view of that data. And so we do that for the two input vectors A and B. They're flagged as const. We're not going to modify them. And the output vector C. Then we have a library-based parallel loop construct, which is actually very similar to what we did for our task-based parallelism as well. And so this should be familiar to users of our earlier work or Intel's TBB. This parallel for each takes two parameters. One of them captures the extent information of a parallel loop nest, so the number of iterations in each sort of dimension of the problem. So in this case, that would be m and n. And then it takes a function closure, which in C++ is called a lambda, and will invoke that lambda once for every point in the implied iteration space, and passing in an index vector to tell you where you are in it. So that's the core data parallel paradigm of, for every point in this space, do this function. Our most significant addition to the language is this restrict keyword, which can be applied to functions and to lambda closures, and it creates a subset of C++ in the body of those functions. That subset defines what is legal to run on a GPU, and it is also a hook to the compiler to understand when multiple implementations are necessary. I'll talk a little bit more about the nature of the restrictions later. Note that the body of the inner loop is essentially unchanged, and we can pick off the row column values out of the index value. The array views are also our hook to understand if you're running in a distributed environment where the GPU has its own memory, what needs to be copied over there and how. Partly that's through what's captured in the lambda. It's also partly how we marshal the array views over. And I'll talk a little bit more about that later as well. Now, because we are running in potentially in a separate address space, potentially asynchronously to the CPU, there's also some API extensions here to talk about what data, if it needs to be moved or doesn't. So the discard data API on C is an assertion, hey, the parallel for each is just going to overwrite this data. So don't bother copying it over to the GPU if you need to. Treat the underlying data as undefined. And at the bottom, there's a synchronize, which sort of does the reverse, saying, hey, this data may have been modified on a GPU, but I want to store it back into its home location in the CPU data structures. Please do that now for me. So this is now an essentially complete C++ AMP program where most of the concepts we've introduced are really kind of around the array abstraction, sort of the size of it. And so it should be pretty straightforward for most of our existing task-based programmers to sort of understand this in its here. Which sort of gets to sort of some of our, I'm sorry, go ahead.
If it doesn't fit, you'll do all the blocking that's necessary to move it back and forth between CPU and GPU memory.
So the question is, if the data that is accessed in the parallel kernel doesn't actually fit into the video memory that's available on the card, what happens? So in our first implementation, it's the responsibility of the developer to ensure that happens. So you'll get an exception that if you exceed it. There is not enough information in general in the API to allow us to automatically block this. Yes?
Can you detect if the discard data was put in incorrectly, like say UIUC after you've said that? Do you have any checks?
So the question is, are there any checks in the system to verify that if you put in a discard data incorrectly and then use the stale data, whether we'll detect that? We don't do that in the first version. So we have this natural tension now between portability and productivity on the one hand and the performance. And this will show up sort of in how much of the machine do we let shine through in the abstractions. So we know that sort of for portability and productivity reasons, you really want to minimize the number of concepts that the developers are exposed to that represent an increment over what they already know. This is just generally anytime a new technology comes from, the richer the set of concepts, the more trouble they'll have to embrace it. And you also need to make sure that they know exactly when it's a good idea to apply that. And so that leads us to focus fairly narrowly on the patterns we're applied to sort of these data parallel constructs. One good composition with the host environment, which is C++, and we've achieved that by having a strong integrated type system that spans both classes of code. And you also want to sort of make sure that you pay attention to the sort of the key patterns that your developer will be facing and give good application pattern support for that. So in this case, we focus on the parallel loop as the pattern we're trying to make sure we have good support. In sort of the more general multicore space, there's lower level support for tasking from which you could build the pattern stuff, but here we focus just on the pattern itself. On the performance side, we're faced with a lot of decisions about how much memory hierarchy, how many memory alignment requirements, what to do with the exposed concurrency between the two kinds of processors to have, and how the hardware scheduling mechanisms might get exposed. These are all areas where the architecture is still considerably in flux. Even today, the range of GPUs are fairly diverse, and since we'd like to have future proofing so that the codes we write today run well in a few years as well, it drives us to sort of minimize the amount of hardware we actually expose. So I'd like to sort of dig down into the bottom 4 of these in the time I have left about sort of some details of what we're attempting to achieve. So let me start by talking about the restrict amp function qualifier. So our implementation builds on top of DirectX 11, which represented sort of an industry standardization of capability, which is something less than what CPUs provide. And so there's a bunch of rules about once you're sort of in the GPU space, what happens. So you have to kind of stay in the GPU space. You can't call back CPU functions. Most of the GPU architectures actually don't support either indirect functions or function calls. And so you have to carve off a subset of the language which you can fully inline and map to that more limited capability. There's typically no memory management and very restricted pointer uses. So these are things that if you look at the most modern GPUs from some of the leading companies have already been relaxed. And we would expect over time to relax this list, and we have a strategy for that. The other thing is this restrict is part of the type system. So we currently have 2 notions of restrict amp for our GPU targeting, and restrict CPU for things that just run on the CPU. Restrict CPU is the default, so if you don't say anything, that's what you get. And you can have overloads, so you can tailor the implementation of function to the context that it's running in. You can also write functions that are guaranteed to be, by a design time, to be safe to run in either function. We anticipate there could be other uses of restrict, so we worked really hard to make sure that it was orthogonal to the rest of the system. Maybe there's restrictions that are appropriate for CPU vector targets. Maybe there's a notion of a pure function we'd want to carve out. So it's intended as a general addition to C++ that we use to enable heterogeneity. We also worked with some of our hardware partners to think about what would be the evolution of this set of restrictions over time. If you go read the open spec at the bottom, there's a roadmap there of likely big buckets of how we might move from our current amp, AMP1, to an AMP2, which would have a subset of this list. So I've already talked a little bit about array view and its role of providing a common namespace between the CPU host and the GPU. The real function of it, however, is to sort of provide copy as needed semantics. So here, if my parallel computation is running on a discrete memory system, then at the time that I launch the kernel, I can observe in the marshaled in the lambda what needs to be copied over. And subsequently, if there's a reference on the host, I can do the appropriate bookkeeping to say, oh no, the current copy's over the GPU, I need to bring it back. On the other hand, we know that we're moving to an age where integrated systems will become the norm. They'll be able to share physical memory, they'll share caches, eventually they'll share cache protocols, and so those copies will become unnecessary. And so we wanted to make sure that we had a system that allowed you to span that transition. So you can write to tolerate a distributed memory environment that will then light up and improve as on an integrated system. We also provide a mechanism to explicitly allocate data on a GPU. So there's an array type. It's kind of analogous to array view, but as a storage container rather than just an access method. And so even today, there's a way to talk about place memory on the GPU because there are scenarios in which that makes sense. A more harder concept where we actually start to say, okay, machines are not as simple as we'd like them to be, and they kind of never have been. But particularly when you get to the memory hierarchy, there's a disconnect between how I want to think about the machine and how it really is. And so we chose to embrace a fairly simple extension, which is, hey, these machines, they're multi-core, and every core has a cache, and you have to provide some mechanism to talk about that locality within an otherwise data parallel context. So this is not a model invented. We inherited it from where the graphics guys were with the X11, but it's a pretty good model, spans a lot of interesting cases, and is a compromise because this part of architecture is probably pretty stable. I don't know what the next stable point in memory hierarchy is likely to be. So we introduced within our data parallel computation space the idea you can break that space into tiles, blocks, what Padua called them. And these are sets of iterations that are going to be mapped to the same physical processor. Now, these physical processors are typically vector processors, so an iteration in our space may actually map to a lane in a vector processor, not a thread of its own, but we will call it a thread nonetheless. Once we have this idea that a chunk of my space can map to a physical processor, we can allow certain capabilities that tend to not scale very well to shine through. And the particular ones are, we introduce a notion of barrier coordination. So all the threads in a tile, all the threads on a processor, reach some point before any proceed. And now we can introduce a notion of shared storage there that is suitable both for sort of temporal caches we see on CPUs, but also as the scratchpad memories that are common as software-managed caches on GPUs. Let me go back to my matrix multiply, remind you that it's easy to do it in a block style, so you can take a block of columns and a block of rows and then accumulate them into a block of the output. So if the block of the output is our tiling strategy for the data parallelism, and we can stage how we do that row column reduction into it. For example, we guarantee that bringing in block 3, we multiply it against block 3 and B and accumulate in the output. Those sub-computations are now things that can fit in a private cache of a multiprocessor. And so this model we then can take forward into the API design as here's matrix multiply in the simple data parallel case that has no manifest memory locality to exploit. And here's the variant of it where we do introduce those things. We introduce a tile size. In this case, it's a static constant. The limitation of the V1 is it must be a compile time constant. We have a variant of the parallel for each in which you take the extent space and you tile it based on these fixed size blocks. So this is just an overloaded parallel for each that handles these sort of tiled extents. We change the parameter into the lambda. Instead of taking an index, it takes a tiled index. A tiled index is a slightly larger thing that has a lot more information related to what's going on in a tiled context. But we can still pick off the sort of global index about where you are in the original space. And so these two variants haven't made any substantive change in the algorithm. All we've done is tile the iteration space into blocks. The more interesting change then is how do we get to the locality? And that involves the following slide, where now we introduce a tile static local variable. So tile static is our second language extension. It's a new storage class. It can only be used inside of a tiled parallel for each. And it allows us to create little arrays which will be mapped into the scratchpad memory of GPUs or will be fit into the L1 caches on a CPU. Now we take our inner product loop, we strip mine it into chunks. So each chunk of that inner product will load blocks from global memory, tuck them into the cache local memory. Then when those loads are all done, it's done cooperatively. Every thread in the tile does one data motion. We do a barrier to verify that all those loads have settled. Then we can drop down into the set of chunks of the inner product. They now read out of cache, protected. And so the effect here is that instead of every thread going to memory for every array reference, there's, in this case, 16-fold reduction in the global memory requirements achieved through sort of this explicit caching strategy. And now a second barrier protects the reads in the inner product from the writes from the next iteration. So this is how we've taken our model of sort of L1 caches attached to processors and put it into the API set for the programming abstraction. Yes, Jim?
What about determinacy? Because you have a sum reduce, which could happen in any order, and in one issue, depending on how things are dynamically scheduled, is that you get the sums in a different order, get a different answer. So is there anything in your language extensions that addresses that?
So Jim's question is about how deterministic is the programming model and this particular example. So this particular example is actually completely deterministic because the output sum is done the same way because it's done by one thread and it's actually done in the same order every time. The concurrency in this model is between different tiles, they're completely unordered. But between different tiles in this model, there's no interactions. A second question is it possible to introduce data races into this model? The answer is yes, it is. For example, if we dropped the second barrier from here, we would create a data race between some threads reading, finishing their sum reductions, and other threads starting to overwrite the shared data that's involved. We actually have some static analysis to detect those data races, and we can run in a mode in which there's some dynamic analysis to detect them as well. But it's not guaranteed to be a foolproof system, if you will. So in deference to time, I'm not going to talk about our compilation and deployment model in depth. We build sort of on the existing graphics infrastructure. We ship a fat binary. We still have a final JIT to target that gives us the great portability across different hardwares, both in the field now and over time. It's a cumbersome model that can lead to fingerprinting, but it does give that core portability that's pretty interesting. So here are the 2 points I tried to cover today. We have a ton of developer-facing information about this tool that's on the web. There's a team blog that you can get to by searching for C++ AMP in a nutshell, or its URL here at the bottom of the slide. And of course, all of this technology is available in the release candidate, so you can go download that today, try it out yourself, see what you like. Any questions? More questions? All right, thank you.